review a little bit what we discussed on Feynman diagrams and what we had actually done. We had discussed the Feynman diagrams, let's say the space representation. So where we wrote all the operators appearing in space representation. Often, of course, it's much better to work with momentum representation because one has translational invariance typically. So the Gaussian propagator, for example, is diagonal momentum representation. So let me just do the review now in momentum representation. So which we will then also typically use for the calculations. So this is because of typically we are considering systems with translational invariance. It's better to go into momentum representation. So what we had introduced was first, so what we have studied was a diagrammatic representation of endpoint correlation functions, and we introduced the external legs or the external vertices corresponding to the operators that appear in the functional average of the endpoint correlation function. Okay, so this was, for example, the eigenvalue of the creation operator, and now this here, instead of carrying an index x, like the point where it's represented, now it contains a form momentum p. In the same way, you can introduce the ingoing leg corresponding to an annihilation operator, which now has some momentum p prime. What we said is if we do a Gaussian average with respect to the free theory, the Gaussian theory, what we have to do to calculate this, I mean diagrammatically representing this contraction of such two external vertices, just corresponds to connecting these two lines. Okay? So now here it means that to connect these two lines, the momentum has to be the same. This is just reflecting again momentum conservation. So we get Kronecker delta here, and then this line would correspond to the free Green's function or the free propagator now in the momentum space. Okay, so for example, the weakly attacking electron gas that we will consider, this free propagator is just given by the Matsubara frequencies minus p squared over 2m. I mean the dispersion relation and chemical potential. So the cases that we will study later on, this will be just given by I omega n plus mu minus p squared over 2m. And here Kronecker delta 7 equals 2 5. Now there's one small thing that you might want to check. So this would correspond to the contraction of an expectation value of this kind, no p prime. And actually when we said that if you have a Gaussian theory, this gives the inverse of the matrix or the propagator, which defines the Gaussian action. But then there is a sign factor, no? Because we said the inverse is given when we have psi and psi bar. Okay, so the sign, and this is why here it appears with the minus p squared over 2m and the plus I omega plus mu. So this is minus, so you can just, if you want, check it. Okay. So this would be just a recontraction of two external legs in momentum space. Then what we had introduced was the interaction vertex. So this is a 4 fermion operator where you have two incoming and two outgoing legs. So this corresponds to the scattering of particles, and now in momentum representation. So now let me also draw the spin. Let's see prime. Okay, so this would correspond now to the interaction vertex momentum representation. Again, we have a translational invariant system, so the overall momentum should be conserved. meaning that we have three free momenta. Okay, so we have here momenta P, P prime, and Q. So Q is the momentum exchange, so we have an electron scattering from P plus Q to P. So the other one has to absorb the momentum Q, so it goes from P prime minus Q to P prime. And if you look at the spin structure, well, you have the same spin here, so it's the same way electron scattering here and here. So this would correspond, let's say, to density of this. Okay? This would be the momentum representation, the interaction vortex. So let's say, so this was the free, this was the interaction vortex. Action vortex. This was the free Green's function, no? Free Green's function. And the line here, in the cases we are interested in, just represents the Coulomb potential E squared over Q squared, where Q is only allowed for non-vanishing momentum because the zero component vanishes. That's the Coulomb action. Okay. So then we have like said, okay, if we want to now calculate, for example, an endpoint correlation function, we should draw the n external legs. Then depending on the order of perturbations here that we're interested in, like in L's order, we would draw L such interaction vertices, and then we have to look at all possible combinations, how we can form out of them diagrams, okay? And in the end, once we have drawn all the diagrams, we have to be careful with the combinatorial factor. We know how many diagrams we should expect, so we can always verify this. And then in the end, we should translate back the diagrams into analytical expressions, always using, well, such a line. Now this is a line connecting external vertices, but you can also have such a line, let's say, interaction. This is always translated into a free Green's function, okay? And this is always translated into the potential. Okay? So you can just translate all this back, where you now have to be, again, taking into account that you will sum over internal momenta. Okay, so these momenta would be fixed by the correlation function, but then you have internal momenta that you should integrate over. Now, there was an overall sign factor that we still had unspecified, and now we can actually say what this sign is. So each diagram for fermions will get some positive or negative sign, just simply due to the fact that we have here the Grassmann variable. So when you do the big contractions, you have to arrange the creation close to an annihilation operator, and this will lead to sign factors. And the rule for the sign factor is as follows. So once you have drawn the diagram, you know that the overall sign is a minus 1 to the power of NL, where NL is just the number of the fermion loops in the diagram, okay? So that's the loop order that we introduced last time, okay? And I think it's also good exercise to convince you maybe of this, if you like, by drawing some low order diagrams. For example, yes, I mean, so we had different diagrams, more like this diagram would have one loop, so this would come with a minus, and this diagram doesn't have any loop, this would come without any minus with a plus sign. Okay? So one has to count the the number of loops to get the sign factor. Okay, so this is all like the rules on Feynman diagrams and already said, so there's different ways how you want to draw them, and if you want to attach already to the diagrams labels, or if you first want to draw them, and then in the end you just give the labels. So this is all up to you. Sometimes one has to be careful to identify that two diagrams are the same, so they are more involved. You can always do like twisting and reshaping of the diagrams as long as you don't do anything drastically as cutting lines. You can try to deform diagrams into each other to see if two diagrams are actually identical. So what we now want to do is actually come back to the problem that we're actually interested in, which is the weakly interacting electron gas, and calculate the free energy perturbatively using Feynman diagrams. However, before we do so, we still need some let's say, observation, which is like a theorem which will simplify our life. So this is what I will discuss first. So that's the linked cluster theorem. And then another thing is, so far we said, okay, so what we do is an expansion in the interaction vertex, but we never really specified like to which order should we go and whatever. And I mentioned several times that this expansion that one is doing is not really like a tail expansion, but it's an asymptotic expansion, so I will comment on that. So maybe in the very end of the lecture we will then return really to the problem that we're interested in the weakly interacting electron gas, but now we are still going like a little bit detour on general things. Okay, so the first general comment on the diagrammatic perturbations here is the linked cluster theory. Which I here state for correlation functions. There is a similar theory for the free energy that we will need later on, but let's first look at the linked cluster theory for correlation functions. And then discuss the second version later on. So this means correlation functions. Maybe you already know it, I don't know. So okay. So even people who know diagrammatics don't know the linked cluster theory. Okay, so this is actually very important. So let's just first start out here with some observation that we made when we calculated perturbatively the first order imperturbation contribution to the Green's function. So what we said in formulas, now I just use the momentum representation. So the Green's function would be this object here. Now we want to calculate this in first order, so this means the first order contribution that we looked at. Okay, so there's two contributions to the first order. One is from expanding the numerator in the interaction. Okay, so this would be this one, so this was expanding here the numerator in the interaction. But then there was a second contribution where we expanded here the denominator and expanded in interaction and linearized this. This came with a minus sign because 1 over 1 plus x gives linearized 1 minus x. No? And this is just okay, so this is actually what we looked last time at diagrammatically. So we saw that this here contains 6 operators, so 3 creations, 3 annihilation operators. So this gives rise to 6 diagrams, and this gives rise to just 2 diagrams. Because we have 2. Actually, when we draw the 6 diagrams, we saw that there is. Okay, let me see if let me just draw them. So what we found were the following diagrams. So we had this diagram. We had, we had this diagram, and then we had twice this diagram, and we had twice this diagram. Okay, so I should put here on max. Okay, so this was by contracting these two, gave rise to these diagrams. And then contracting this with the interaction gives always a combinatorial factor 2 because there's 2 ways you can connect this to one of this and get these diagrams. Now these diagrams here, just while you contract these two, you get this diagram, and then you get the second version, which is this diagram. Okay, so this is just because So what you see is when you take the difference of these diagrams, well, these just cancel, okay? So what you survive with is only these diagrams which we gave a name. So this is a diagram which are connected, and actually these are also diagrams which don't contain any vacuum diagrams. So if you're looking at two-point correlation function, the notion of non-vacuum and connected is identical. However, once you come to higher correlation function, it doesn't have to be. So we see some cancellation, which is nice, which simplifies the things, and actually this doesn't occur by chance, and this is the statement of the link cluster theorem. So the link cluster theorem states that if you do the expansion of the numerator and the denominator, there will be a large constellation of many diagrams, and actually it will always, you see that if you make the expansion of the denominator, what you end up here is always with expectation values of the interaction vertex isolated without connecting to any external legs. And these diagrams are not diagrams that we call vacuum diagrams. So what happens actually is, if you expand the denominator, what will happen is that you generate a lot of vacuum diagrams, and it turns out that these vacuum diagrams exactly cancel all the vacuum diagrams that you can generate from such a correlation function. So this is a huge simplification, because this means that if we're interested in an endpoint correlation function in nth order, all that we have to do is we have to look at the contribution from the, let's say, the denominator, and there only draw all the connected diagrams, because we know that the vacuum diagram, I should say the connected, we should always the non-vacuum diagrams. Okay, so for Green's function it's the same, but high correlation function. So we should only draw the non-vacuum diagrams, because we know that the vacuum diagrams will be cancelled by a cancellation of expansion of the denominator. So that's the statement of the cluster theorem that we just write once down, and then we all prove it. So the contribution to a correlation function here, general endpoint correlation function, which now that we change the momentum representation depends on 2 and 4 momenta. At the nth order, of perturbation theory, is given by the sum of all diagrams or graphs excluding the vacuum diagrams or graphs. And again, vacuum diagram or vacuum graph we define as diagrams of graphs which have the interaction vertex not connected to external legs. So this is a very important thing, because this tremendously simplifies our life. So in practical terms, stated a little bit different. In practical terms, this means that if we do the perturbative expansion, only the non-vacuum contributions or diagrams the expansion of only the numerator have to be kept. Okay, so that's a recipe that we should always recall. Okay, so that's a statement. Let's look at the proof. or is it? Statement is clear, no?
Questo è vale per qualquer faixa de energia?
Para quê?
Para qualquer faixa de energia.
Sim. Isso é só um statement. Bom, a gente vai ver a prova. Até agora é um statement para a correlation function, mas a mesma coisa existe para a free energy, que a gente vai precisar para o cálculo que a gente está interessado. Só que a prova para free energy pode ser um pouco mais complicada, mas existe um truque como provar esse statement para a free energy, que é baseado no replica trick, que eu acho bem bonitinho, e a gente vai discutir isso provavelmente num exercício. Bom, então isso agora é para correlation function, mas existe uma coisa parecida para a free energy que a gente vai discutir. So, the proof of doing cluster C. Okay, so let's start out from a general, generic expectation value in terms of fermionic variables, psi bar psi. So this can be anything like an endpoint correlation function, which we said we can express in terms of some series. Where we expanded just the interaction term, the numerator and the denominator. Okay, so this is just how we define this expectation value. Well, we can express it as a series in expectation value with respect to the free theory, where we should expand the interaction versions. Now, let us consider, so we have expanded the numerator and the denominator, so let's consider the nth order contribution. Nth order, giving the nth order in the interaction from the numerator. So maybe we should have call this M just to not make any confusion. Okay, so let's look at the nth order contribution from the numerator and think what we will do. Well, we will write this as like the quantity of external legs, it's determined by x, and then n such interaction vertices, and just draw all the diagrams. And then what we will start is doing the big contractions by connecting the external legs and the internal legs to generate three Green's functions. So these contractions will lead to some of vacuum diagrams let's say of p-th order, and then the remaining n minus p order will be non-vacuum diagrams. And non-vacuum diagram of p-th order, and the non-vacuum diagram of n minus p order, where, well, p can run between 0 and n. So this means that the nth order contribution will look as 1 over n faculty. Then here's a combinatorial factor that I will comment on, and then I just write in formulas what we said. So there will be diagram of n minus pth order, which is nv for non-vacuum. And then there is pth order vacuum diagram. Okay? So that will be the contribution in nth order. So this here means non-vacuum. And this here, of course, doesn't have any external legs connected to the interaction vertex, so this will be vacuum diagrams. Now, this factor n over p is just a combinatorial factor which tells you in how many ways can I draw p, like terms out of a whole set of n terms. Okay? So this tells us like in how, this is just a combinatorial factor. We draw n interaction vertices and we have to choose out of the n p that we want to lump into the vacuum diagram and n minus p into the non-vacuum. And this is just a combinatorial factor which accounts for this possibilities, the number of possibilities that, that we can do this, okay? So this is choose the combinatorial factor to choose p out of n vertices which we want to lump into the vacuum diagrams. Okay? So now we just have to recall what is n over p, when n over p is n faculty divided by p faculty minus n minus p faculty, so the n faculty cancels out. Okay? So this contribution here will just remain a 1 over p faculty and 1 over n minus p faculty. Okay? So now if we return here to the denominator, what we will have is we have a sum over n and sum over p, which each contribution we can write in this form. Okay? So we see we have a product of two terms. We have an n minus p with a prefactor 1 over n minus p faculty. And we have this term with a p faculty. And we have a sum over n and over p. So let's just redefine the sum over n as a sum over n minus p, calling it k. Then we will have a sum, double sum over k and over p, where the k is as follows: 1 over k faculty, x as int to the power of k, with non-vacuum diagrams, and then we have a remaining sum which is 1 over p faculty with s in the power of p. Okay, so if I just do this here, so the numerator here is just given by sum over n, sum over p. And we said, okay, I probably do it in too much detail, but just have it done once. So this is just copying what we said here for the nth contribution. We can write this as p such terms. No, and p runs from 0 to n, and n is what. So now we said that this here is nothing else but 1 over p faculty, n minus p faculty. So let's call n minus p faculty k, and then we arrive at sum over k, sum over p, 1 over k faculty, as int to the power of k, x as int to the power of k, 0, and I should not forget here the non-vacuum. Okay. And then we have here still 1 over p faculty as int to the power of p. 0. Okay. Now this doesn't depend on p, so let's write the sum from here to here. Okay, so this was an expansion of the numerator, but now we see, well, that this here is nothing else but this here. Okay, so if we now divide this by the denominator, we see that this term just cancels out against this, and what we are left with is the sum over all powers in the interaction, where what we have here is the non-vacuum diagrams. Okay. This cancels against denominator, and this means that we are left with this here being just what we wanted to show. This expectation value is sum over k, sum over k faculty, of k. So this would be what you get just by expanding the numerator, and what we should keep is only the non-vacuum diagrams. Okay, so this is the statement written here and here. What we need to do is only expand the numerator and keep the non-vacuum diagrams. Okay, questions or? Okay, and again, this is really a very, good news for us, because this really helps a lot our life, because we stick to this procedure to calculate quantitatively or diagrammatically endpoint correlation functions, only expand the numerator and keep the non-vacuum diagram. Now, this was the first thing. It's important technical remark. Now, the other technical remark that I just mentioned early on is, well, we always wrote here something like a sum over n, sum over p, but I never really specified what it means. Here actually what we use is kind of Taylor expansion, where really m runs from 0 to infinity. Now, Taylor expansion is something that, we know from mathematics and that we like, but actually here in this kind of problems that we are facing, one has to be careful, because quantitative expansion actually in most cases will not be just a simple Taylor expansion, but it will be what is called an asymptotic expansion. So again, it's something like where mathematics and physics go different ways, but let me just first illustrate the problem at a simple example. The difference between asymptotic and Taylor expansion, and then in the end tell you why in the end we shouldn't care too much about this difference, because in practical terms it often, the difference can be relevant, but doesn't always have to be relevant. And again, it's a thing which you should keep in mind, and you can start doing what you're doing in weak order perturbations here, or weak interactions, but always it's good to recall if something very strange is happening, like that there's always some caveats in the machinery that we are applying. So this is just a warning on asymptotic and not Taylor expansions. So, did you discuss this when you discuss perturbation diagrammatic? Do you know the concept more or less? So, also I don't give anything very profound, but I will just illustrate the idea on, let's say, and caricature of some interacting theory. So let's try to make things as simple as they can be, and let's consider the following integral. So this is like, let's say, caricature of interacting theory. Caricature, I don't know how to say it in English. In German it's caricature. Of an interacting theory. So why? Because it's just the typical integrals that we find. So here now it's just integral over real values. So this can be like real bosonic fields or complex, or it can be generalized. But what we typically encounter is the following. We have the quadratic term, which would describe the non-interacting or free theory. So that's a reference point around which we organize our perturbation theory. And then we have an x to the 4 term, which would typically represent some interaction. So if we do perturbation theory, we take this as a reference around which we organize everything and expand in this interaction term. Okay? So this is what we're doing, and the problem appearing in general, like in these kind of interacting series, so the more complex can be already illustrated here quite nicely. So the basic idea that we have when we formulate our perturbation theory, the basic idea is that we say, well, if this interaction coupling here, if the coupling strength for the interaction is small, yeah, let's say that here you have a dimensional parameter which is much smaller than 1, well then it seems like a very good idea, or it seems natural to treat the interaction which we call the x to the 4 contribution, so the interaction will be the gx to the 4 perturbatively. Okay, so that's the entire idea that we have been using so far. And mathematically, this means that we can try to calculate this integral as some series starting from n equals to 0 in powers of this interaction strength, or the coupling constant. And then integrals I, which depend on the order of interaction that we look at. So Gn, In would be minus G to the power of n divided by n faculty, and then the integral to I x to the 4n. Okay? So this is just what we get if we expand this powers of G. And all that we have been always saying is, well, we start at some n equals 0. If it was a Taylor expansion, we would expand this up to infinity. Okay? So now what we know about what we have learned so far is, well, this is just a simple Gaussian integral where we calculate, let's say, for endpoint correlation function, you have a real bosonic field. So we know what this gives. So if this was fermions, we said, well, we have to see how many ways we can contract. Like if we have here 4n contributions, we would have 2n creation, 2n annihilation operators. This would give us 2n faculty possibilities to contract. Now, if we have this kind of real bosonic fields, actually we said again what the rule is. Like you have to look at all the possible pairings. Yeah, so you can contract, let's say, this with this one, this with this one, this with this one, okay, or this with this one, and so on. So if you go through the combinatorics, so this has like if this is n terms, this has n minus 1 terms you can pair up with. Okay, so let's pair this up with this. Then let's say this one now has n minus 3 terms to pair up with. Okay, let's pair this with this. This has an n minus 5 and so on. Okay, so what we get is n minus 1 times n minus 3 times n minus 5. And this is also called n minus 1 double faculty. Or is it called n minus n double faculty? Actually, I don't know. No, it's n minus 1 double faculty. Yeah. Okay, so it's like double faculty means that you jump like one. Okay, so if we recall this rule here, we can readily see that this here is given by minus g and faculty, and then we have here the sum over all possible pairings of these four n objects. And this, let's try to convince you, gives you minus g to the n and faculty, and then the 4n minus 1 double faculty. So 4n minus 1, 4n minus 3, and so on. But now you can already get kind of a little bit scared, because this is going to get, as n is large, this is going to be a very, very large number. Okay? So actually, if you use that n is a large number, and you can use like Stirling's formula, which says, well, for n large, you can approximate this by n to the power of n and e to the minus n. You can estimate this, so maybe I leave this as an exercise. Actually, that this, for n being much larger than 1, using Stirling's formula, okay, you can show that the combinatorial factor from the 4n minus 1 faculty and the n faculty here will give you a remaining n to the power of n. Okay? This is like based on this kind of estimates. Okay? Now this means actually something really bad for us, because we said in the beginning, well, let's try to calculate this integral, assuming that g is small, everything should work out. But what we see is, well, everything doesn't work out, because how small g is we start out from. If we only get to very high orders in the perturbation theory, at some point this n will just overweight the small number 1 over g. And then this is larger than 1, and this will just completely explode. Okay? So that's the first observation that we do, that the idea, well, g is small, let's do an expansion g, doesn't really work out, because we see that no matter how small g is, at roughly the 1 over g's order in perturbation theory, so where n is of the order of 1 over g, this is becoming of order 1 and will just explode. So at some order, the series just begins to diverge, and we are left with very bad news, that the kind of idea that we had in the beginning, that there is some expansion in the small parameter, just does not exist. So the idea that we had mathematically just doesn't make any sense. And actually, if we look into this integral, we could have guessed this from the beginning. So mathematically we see, I mean, this expansion, this series that we wanted to do, Taylor's series, does not exist, because there is an order n when this blows up. Now, if we look at this integral, we could have guessed this actually from the starting, because we said, let's look at this integral and let's make a perturbation theory in G. Now, if we look at this integral, we see, well, this integral is perfectly fine for positive g. But if g actually is negative, this integral doesn't exist. Okay, so this just blows up, doesn't exist. So this integral has to have positive g. Now, what this means is what we are trying to do here is just a Taylor expansion of this function around g equals 0. But if negative g, for negative g, this integral doesn't exist, this means that the convergence radius around g equals 0 is just 0. And this is just what's happening here. Okay, so we cannot do any perturbation theory in g equals 0 because it doesn't exist. This is a function which you might expand around g, but you should expand it around positive g. There is a positive convergence radius, but if you try to expand it around g equals 0, it doesn't have any convergence radius. It's 0. Okay? Okay, so this is just what is happening here. Now you can, okay, maybe I just write it down. Series expansion of this integral around, let's say, the non-interacting expansion point has 0 radius of convergence. And this again is like, at first, very bad news for us because of course we want to use g equals 0 as a reference point because this would correspond to then it's like developing the theory around the non-interacting theory which we have under full control. So we know the propagator of the non-interacting theory, but we don't know the one of the interacting theory. Okay? Now you can also make this observation made here in mathematical terms. You can also put it more physically. So what is happening here is the following. You have a competition of two things that is very typical to occur. So we say if we go to high orders in an expansion here, the g will appear with higher and higher orders, okay? So this will become smaller and smaller, so that's fine. However, what we neglect here is that in the perturbation theory, we will have to do like the contractions of all these terms. And there is a very large number of ways how we can build up diagrams in hence perturbation theory. So there's a competition between the small factor here as we go to larger orders in perturbation theory. This becomes smaller and smaller, but there is, let's say, an entropic factor, yeah, which just completely blows up and at some point will just overweight this contribution. Okay, so there's again like a little bit this competition between like the small and small interaction strengths, but there's some entropic factor which will just blow up. More physically, so that was the mathematic statement on this kind of expansion that we are doing. More physically, what is happening is that you have a competition between small per meter g to the n and a large combinatorial factor proliferation of contributions. Y minus 1 after factor t. And at some point, this exponential growth here will just overweight this Aula decay. Okay? So that the combinatorial factor just explodes exponentially at some point, will win this popular suppression. So this looks at first like a bit, you're really in a bad situation because if you cannot do any perturbation theory around the non-interacting reference point, you at first don't really know what to do at all. So the only thing that we really have under good control is the harmonic oscillator, and it's like a non-detected problem, and everything that is beyond, like, so if you cannot organize it this way, this would be really bad, but actually it's not as bad as it looks at this moment. And the idea is, okay. However, situation is not as bad as it might seem, and the way out is actually to do what I have mentioned before. So let's, instead of considering the formal Taylor expansion, let's define something like a partial series, PS for partial series. So where we look at the integral where we start our expansion, but we expand not to infinity, but only to some maximal order n max in the attention term. Okay? So let's see what this gives us. So the idea is, if we choose this here cleverly, then actually what we get for the partial summation, this gives us an excellent approximation, or does not always have, but it can give a very, very good approximation of the original integral. What we will see is, well, this m max we saw already has to do with like 1 over the inverse coupling constant. Okay? So if we have small coupling constants, this will be a large number. And what you can show that in this case, this partial summation gives an excellent description of what you want. And this will be the weakly inflecting cases. Okay? Now, if you would go beyond this maximal value, then you will just start to diverge and you get worse and worse. So there's some maximal, let's assume there's some maximal number which gives us the best approximation of the integral that we're interested in. So let's first look at this. So we define the partial summation, and what I now want to convince is that this can give excellent approximation. So again, what we do in this physics, we don't have to get the completely exact result, get a good approximation, we're already happy. And this can give an excellent approximation to the exact result. So let's see this here the following way. So in the integrand of the real integral that we want to calculate, we have the exponential of this here. Okay? Now, if we approximate what we do, if we do such a partial summation, what we do is, instead of writing, so this is equivalent to a Taylor expansion. Okay? In the partial sum, we do not use a Taylor expansion, but we use only the partial summation up to some maximum contribution here. So if we take n max to infinity, well, then this just gets 0. But we can estimate this because we have just a changing sign always, and then like a decreasing term here. We can just approximate this by estimate this by the next contribution that will appear here. So this will be smaller, the difference will be smaller than n max plus 1 divided by n max plus 1 factor. Okay? It's just estimating the mistake that we do when cutting off this integral. Well, you can estimate it by the next order because then it's a changing sign. Okay? Now, what this means is that if you partial summation and look at the mistake that we do when not taking into account all terms but only up to an n max, then this integral is smaller or less than dn max plus 1 divided by en max plus 1. Okay, so that's the integral. And this, if we already anticipate that n max is much larger than 1, then we can use our estimate that we had before. So n max is much larger than 1, which we should confirm self-consistently later. Then we can just express this as what we found. So this is g times n max. Now it should be n max plus 1, but if this is much larger than 1, we can just call it n max divided by e. Okay, that was what we found, to the power of n max. That's hard to write. N max. So this is just under the assumption that this is much larger than 1, and we will see that this is actually the case if g is small. Okay. Now what we can do is, now that we, just made estimates. So let's see if we use this, we can find that the partial summation, well, the accuracy to which we can approximate the integral that we're interested in depends on n max, and it can be estimated under this assumption by this. So now what we can do is we can just try and minimize the error that we are making. Okay, so the error that we're making is smaller than this, so we can minimize this with respect to n max. Okay? So once we have found the minimal value for n max, we can put it back in here, and then we can see how small this mistake gets. Okay? So what we can do, again, it's like if you like to do it at home, just you can do a variation with respect to n max, which would be the best choice for the order to which we should do the perturbative expansion. And if you do the variation with respect to n max, you find that the error reaches its minimal value when n max is of the order of 1 over g. Okay, so this is just from experimenting, and then we see, well, if you're in the recoupling limit where g is small, then this is n max much larger than 1, so that's self-consistent, that's all fine. So we're considering g small from the start, so this is fine. Now, it's also clear that this has to have a minimum, because if we just start with zeroth order, we know that first order will be better than zeroth order and so on. And then, on the other hand, we know that at very large order, this starts to explode. So this is like this error is getting smaller and smaller, but it's somewhere exploding somewhere up there. So there has to be a minimum, and we just can figure out that this minimum is 1 over g. Now, if we plug this in there, then we find that at the minimum variation of error reaches and where this integral, so the difference between the partial summation and the true integral reaches a value of what e to the minus 1 over g. Okay? So this is then very good news, because if g is a small number, well, this is a very, very good approximation. Okay? So we see that going beyond a given order n max doesn't make any sense. Our result gets worse. But if we stick to this maximum value, we are quite well approximating the original integral. Okay? So we just summarize So if we start out from a weakly interacting theory that we had in mind, so where the coupling is small, then actually it turns out that partial summation instead of a full Taylor series, a perturbative series, can lead, or typically leads to, very precise approximation of the exact result. And just to give an example, well, if G, for example, is 0.1, then one has to go to the 100th order in, one should go to the 100th order in perturbation theory, and this is then correct up to, well, e to the minus 100. Just as an example, in Q and D, the coupling constant is 1 over the 3. So this definitely falls into this idea where partial summation should be fine. And I mean, as a physicist, if you hear like go to the 100th order, I mean, for us it's just an academic, I mean, distinguish between Taylor expansion and asymptotic expansion just is academic. I mean, it's of interest for mathematicians, but I mean, 100th order of, and the error also, I mean, e to the minus 100. Okay, but huh? But still, I mean, it's always too good to keep this kind of things in mind, that if something strong, I mean, weird is going on, you should keep in mind that a perturbative expansion is always an asymptotic expansion and should not be confused with a Taylor expansion. With something rigorous like a Taylor expansion. And well, while this is really not a role for PD, if you look at theories at intermediate or strong coupling, where G is not that small, well, there definitely one has to keep this in mind. Coupling, and for intermediate or strong coupling theories, the asymptotic character of perturbation theory should always be kept in mind. Okay, so that was the warning on asymptotic expansions, and then let's see. Okay, I mean, we're jumping back and forth, but finally we'll get like what we want to do. So then let's make a short break, and then we'll return to the free energy of the weakly interacting electron gas. You can already start looking at the first diagrams, but